When it comes to searching for buried treasure, any child who's ever dreamt of being a pirate or a great adventurer can tell you X marks the spot. Later in life, bags of doubloons and rubies are a little harder to come by, but we're still on the hunt, this time for answers. Today we've traded in our treasure maps for graphs. There's a wealth of information hidden where two equations have the same solutions, and graphing and seeing where two curves intersect can guide us there faster. Now, some of these intersecting questions show up where you might expect, like in high-stakes decisions made by people such as economists, contractors, or air traffic controllers. But they're also woven through the fabric of everyday life in the form of crisscrossing linear equations, or equations that describe a relationship between two variables where we can multiply one variable by a constant to get the other. We call them linear because they form straight lines when we graph them. Linear equations, like a compass to our fearless swashbucklers, are essential to algebra and describe fundamental relationships like the ones between distance, speed and time, or price and cost. So let's see what clues we can dig up and how we can solve equations just by graphing. G'day, I'm James Tanton, and this is Study Hall Algebra, presented by Arizona State University and Crash Course. Linear equations show up all over algebra, so it's easy to feel like you either already know everything about them or like you should already know everything about them. But neither of those things have to be true. For example, here's a surprisingly hard question to answer. What makes a straight line straight? Now we can close our eyes and imagine a straight line or just draw one with a ruler. But how do we describe that picture in the language of math? Now, we can start by looking for patterns that are unique to graphs of lines. For instance, look at the angle between the line and any other horizontal segment. No matter where you are along that line, that angle will always be the same. And compare that to a graph of a quadratic equation, that angle keeps changing. Or we might notice how the line moves across the plane. If I were to run a fixed distance to the right, no matter where I started, I would have to rise the same amount each time to get back to the line. And if someone doubled my run, they'd have to double my rise. So, to answer our not-so-obvious question, a line is straight if the ratio of rise over run, which we call slope, is the same number no matter where you choose to measure that ratio along the line. You can also think of the slope as measuring steepness. This line has a sharp slope of 4. This line has a gentle slope of 1/2. If the rises and runs we draw look like an up staircase from left to right, we have a positive slope. If they look like a down staircase, then we have a negative slope. Now, textbooks give this formula to find the slope of a line. There's really no need to memorize it. After you pick any 2 points on your line, the bottom part tells you how far you've run, and the top part tells you how far to rise. And the line is straight if we get the same ratio no matter which 2 points we pick. Now, there are two types of lines that cause trouble in the slope department. One is a perfectly flat, horizontal line like this one. This line represents all the points that make the equation y equals 3 true. So no matter where I start, if I run some distance to the right, how far do I need to rise or fall to get back to the line? 0. I never left. So the slope of a horizontal line is 0. The second challenge is in the other direction. Start at any point on this vertical line and run any distance to the right. Now try to rise or fall back to the line. We'll never get there. Vertical lines break our rules for slope, so we call the slope there undefined. But since this is a valid line, the language of math is still able to talk about it. In this case, this line represents all the points that make the equation x equals 5 true. Now, if you've taken an algebra class before and someone leapt out of the crowd demanding you tell them about graphing linear equations out of sheer muscle memory, you might say, y equals mx plus b. But the person next to you might remember getting something about the slope from 2 points. Another person might remember some equation with a, b, and c. From the sound of it, we've now got a whole scatterplot of knowledge. But in fact, we're all talking about the same thing. It turns out there are lots of ways to write linear equations with math, and they're all useful in different ways. But I'll be straight with you. This is just one of those things we have to learn, like different tenses while learning a language. Math is a language too, so with practice you'll learn to recognize these forms. Now, in a textbook, we might see something like, find the equation for a line with slope 2 that passes through the point 3, 4. Okay, we could put those pieces into our slope equation. For any point x, y on the line, the rise over the run must equal 2 over 1. And we can plug in 3, 4 for one of the points in the formula. Then y minus 4 over x minus 3 equals 2. Okay, this is a fine start for an equation, but it needs some adjustment. The way it is now, it actually has a fatal flaw. We're told that 3, 4 is on the line, but if we plug in x equals 3, what happens? Oh my goodness, we're dividing by 0. Now we can get around this flaw by multiplying both sides by x minus 3 and use the equivalent equation y minus 4 equals 2 times x minus 3 instead. Now, even the point x equals 3, y equals 4 gives a true sentence. Crisis averted. Because we built that equation up from just a single point and the slope, that general strategy is called finding the point-slope form. But thanks to how graphing calculators work, and because we tend to like pictures, you might be more familiar with the slope-intercept form. In the slope-intercept form, some key parts of the graph are actually easy to visualize from the equation, like the slope and the y-intercept, or the point where the line crosses the vertical axis. Now looking at our horizontal axis, we can see the y-intercept is always where x equals 0, and that's how we can solve for it. If we already have the point-slope form, we can get the slope-intercept form pretty easily by putting everything except the y on one side. The slope of the line is 2, and if we plug in x equals 0, we get the y-intercept, -2. There's one more linear equation form, standard form. Here we rearrange the equation so we get all the variables on one side and all the constants on the other. Now standard form is useful because it doesn't focus on slope, and we can still use it for those pesky vertical lines. For example, the line x equals 5 is really 1x plus 0y equals 5. And it was in standard form all along. So linear equations can come in a few different forms, and no form is inherently better than any other. You can write it as y equals mx plus b, or ax plus by equals c, or some other clever way you like. Mathematics cares more about representing the truth than about convention. Or you might switch it up depending on the situation. For comparing two lines, we might choose a form where the slope is clear, because it hints at how those lines behave together. For instance, we can think of two lines with the same slope as moving at the same pace. If I start on a line and run 1 unit to the right and then rise 2 units to get back to the line, I'll have to do the same thing on the second line. The two lines will never intersect and are parallel. Perpendicular lines are somewhat the opposite. They cross at a crisp right angle. Here's a line with a rise of 3 and a run of 2. Rotate the picture 90 degrees and we get a perpendicular line. Now it has a run of 3 and a rise of -2. In general, perpendicular lines have slopes with opposite signs that are reciprocals of each other, meaning if we know the slope of one line, we can flip the fraction and swap the sign to get the slope of the second. So, if we have two or more equations in point slope or slope-intercept form, we'll be able to tell right away if the lines are parallel or perpendicular before we've done any graphing. So what about lines that aren't parallel or perpendicular? If they're not parallel, well, they must intersect somewhere. And the trick is figuring out where. In fact, hunting for the place where x marks the spot, or where two curves intersect, is a big deal in math. Not just with linear equations. Instead of chests of gold, the spot where two curves meet is a treasure trove of information. Whatever relationships we're graphing, they only have the same values where the lines cross. Finding these intersections is actually solving simultaneous equations, which are sets of two or more equations that all use the same variables. We're looking for the values that make those equations true at the same time. If we have to solve by hand, this is standard form's chance to truly shine. But we can usually find the answer just by graphing instead. So let's start our treasure hunt with a word problem. How many gallons of 50% salt solution and how many gallons of 10% salt solution would have to be combined to make 4 gallons of 20% salt solution? But wait, this is word problem déjà vu. We've solved something like this before with pictures. Now we can try it with graphs. So let's focus on this through X, Y, and grid ray vision. We know we need to end up with 4 gallons of solution that's 20% salt, or has 4 times 0.2 equals 0.8 gallons of salt. And to graph, we'll need to turn our information into equations. Now I'll call the amount of 10% solution we have K for kinda salty, and the amount of 50% solution V for very salty. Then K and V added together need to sum to 4. Now we need a second equation to bring in the salt. The amount of salt from the kinda salty solution will be 0.1 times K, because 10% is salt. And the amount of salt from the very salty solution will be 0.5 times V, because it's 50% salt. Added together, that's our total amount of salt. We're more likely to make mistakes with decimals, so let's multiply both sides of this equation by 10 and get an equivalent equation. To start plotting, let's put V horizontally and K vertically. If we find the V and K intercepts, we can use those 2 points to sketch the line. That's easy for the first equation. And the K intercept for the second equation is pretty easy too. When V equals 0, K equals 8. But what about the K intercept? When K equals 0, V equals 8/5. I mean, that could work, but integer data is much simpler to work with. Instead, we notice that when V is 2, then K has to equal -2. Now, does that make any sense in the real world? Nope. We can't have negative volume. But it's fine to extend our math to help us out. And the drumroll moment, do they intersect? They do. And our answer sounds familiar from our last salt scenario. 1 gallon of 50% salt plus 3 gallons of 10% salt equals 4 gallons of 20% salt solution. So, for the second time in a row, we've solved a solution-dilution problem just by drawing a picture of its relationships. But this time we did it a little more formally. And we can use this graph to get other information about the situation, like if we want to adjust the ratios. Now, if you are asked to find the equation of a line, even buried in a word problem, here's some starting points. The slope formula is just finding the rise over the run between 2 points. Use it to find an equation for your line, whether you already have 1 point and the slope, or just 2 points. And if you're solving a system of linear equations, graph them and see where they intersect. And a quick way to get a couple of data points to work with is to set each variable equal to 0. Next time, we'll look at the graphs of other equations we haven't drawn yet, like logarithms, and see what else we can learn from graphs to help us in the real world. Until then, cheerio. Thanks for watching Study Hall Algebra, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video and want to keep learning with us here in Study Hall, be sure to subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. So I'll see you next time.